Hello, physics students. I am Mr. Williams, and so we're going to do a quick review about electromagnets, and then we're going to talk about generators. Okay, so remember, if you put electricity down a wire, you're going to create a magnetic field, okay? If you take that straight wire and you form a loop, it's going to be a stronger magnetic field, okay? If you if you take that same loop and then you make many more loops into a coil, you're going to have an even stronger magnetic field. You put those loops all around a metal bar, and then it's really strong, right? And so what we need to know is electricity going down a wire creates a magnetic field. Well, what do we know about magnetic fields? Magnetic fields have a north and south pole, okay? Opposite poles attract, the same poles repel. Okay, north and the south would attract, and a north and a north would repel, for example. Okay, so that's the electromagnet. As long as electricity is there, it will be magnetic. Remove the electricity, it's no longer magnetic. So an electric current causes a wire coil to produce a magnetic field. The electromagnet's magnetic field is either attracted or repelled by the magnetic field of permanent magnets. And that's what we have here on this image. The electromagnetic coil can be built on a shaft that allows it to rotate. Okay, so the coil is designed in a way that it can spin. And this is the simplified basis for the electric motor. Okay, there's some design elements called a commutator that allows the current to switch directions so it can keep on moving. But that's how a motor works. Well, today we're going to be talking about how a generator works. Well, a generator works just like an electric motor. An electric motor is a generator, but what's the difference? Electric motors, you're going to add electricity to make motion. Well, electrical generator, you're going to use motion to create electricity. Okay, so let's talk about it a little bit more. Okay, moving a loop of wire through a magnetic field causes an electric current to flow through the wire. All right, so all you have to do is move the wire through that magnetic field, so you're providing the motion of the movement, and then electricity is generated. So moving a magnet through a loop of wire also produces current, and I'll show you an image of that in the next slide. So the mechanical energy of the wire loop or magnet is converted into electrical energy in the form of current. Remember, mechanical energy is potential and kinetic energy, right? So we can just think of movement or the potential to move. So we can cause, if we do the moving of the magnet or do the moving of the loop while that loop is next to magnets, then we create electricity. The movement of the magnet and wire loop relative to each other produces the electrical current. So this is called electromagnetic induction. It's the process in which electric current is produced in a wire loop by changing magnetic field. This is a super simplified form of this. Is you had a wire loop and you just took a bar magnet and you kept poking it through the loops, you're going to get a little bit of a electrical current produced, right? If you go one direction, you're going to produce the current to go in one direction, and if you pull the magnet in the opposite direction, you'll cause the current to go in the opposite direction. So this is a good image of a generator. Generators provide most of the electrical energy used in everyday life, okay, except for batteries and solar panels. Everything else uses a generator. A generator uses electromagnetic inductions to transform mechanical energy into electrical energy. Remember, that electromagnetic induction is you are spinning a wire coil in a magnetic field, or spinning the magnets that are holding the magnetic field in a electrical coil. Okay, so the image here, what we see, okay, this red part would be a north or south pole. The green would be either a north or south pole. They're not labeled, but they're different poles. And then we see the magnetic field lines. These blue lines going down are magnetic field lines. This red wire that's in the shape of a square, let's think of it as a bunch of loops, okay? And the bunch of loops are attached to these rings. These rings are called commutators. And you got to attach it to something or the wires would just get tangled up. And so they're connected to these commutator rings that allow it to help spin. And then it's attached to a wire. This little device here is a resistor. Don't worry about it. That's a advanced device just to make sure it keeps the same amount of electricity flowing. So this orange yellowish part right here would be like the hand crank. If you keep on cranking it, then that loop will continue to spin through that magnetic field. The idea is as simple as it really sounds. If you spin a wire loop through a magnetic field, you're creating electricity. It's as simple as that. And we see this voltometer here. You can see the current is changing directions as it goes to negative to positive to negative to positive. And the reason why that's happening because as you're turning it, one side of the wire is going through the north side of the magnetic field, right? That same piece of wire, when it's flipped 180 degrees or it's been flipped upside down, it's no longer facing the north side. It's now facing the south. And so as that wire spins through north and south, alternates as it goes through north and south poles, it changes the directions of the current. This actually produces something called alternating current. Okay, the current is alternating from one direction to the other, and that's because one side of the wire, at one point, it's facing the north magnetic pole of the magnet, and then it faces the south magnetic pole of the magnet. Since it is alternating which side of the magnet it is going through, or which side of that field is going through, it alternates the current. That's where we get alternating current, AC current. Okay, and so I pretty much explained this now of how we're switching directions as one side of the wire faces a different side of the north and south pole. And so we'll explain it here again, and if hopefully it'll come together for you. As a generator's wire coil rotates through the magnetic field of the permanent magnet, current flows through the coil. After spinning half a turn, the coil moves past the opposite ends of the permanent magnet. Okay, it goes to the different pole. This causes the current to change directions. The direction of the current in the coil changes twice each pole rotation. So what I want you to know is as you're turning this, one side of the copper coil is at the north side of the permanent magnet, and as it turns, then it'll go to the south side, then it'll go to the north side, then it goes to the south side, and this causes the electric current that is created to alternate the direction it goes. So this is the electromagnetic force. A changing magnetic field can cause electrical charges to move in a wire. So it's an electromagnetic force. That's the name of it. Also, a moving electric charge produces a magnetic field. Okay, so now we know that if you add electricity to a wire, you're going to get a magnetic field. If you pass a magnetic field through a wire, you're going to get electrical charge. It's just two of the exact same force. The magnetic field around a permanent magnet is due to the motion of electric charges in the atoms. Electric force and magnetic force are two different aspects of the same force called the electromagnetic force. Electromagnetic force exists between all objects that have electric charge. The electromagnetic force can be attractive or repulsive, depending on the pole orientation. So in our homes, electrical energy comes from a power plant with huge generators, just like the generator I explained to you. Okay, they're bigger and more more industrial, but that's what they use. The coils in these generators have many coils of wire wrapped around a huge iron core. Remember, the more coils you have, the stronger the magnet will be, the more turns you have. The rotating magnets are connected to turbines, and we're going to see a picture of a turbine next, okay? Turbines, a large wheel that rotates when pushed by wind, water, or steam. Okay, and this is a image of a turbine, okay? So steam shoots through these fan blades, and as steam goes through the fan blades, they spin, and they are connected to basically a shaft, a pole. As it spins, it's connected to other magnets. These magnets spin past a bunch of copper coils, and then those copper coils, electricity is generated through them, and they eventually send them to your house. Okay, so some power plants use heat to boil water to produce the steam that turns turbines. That would be coal fire plants, nuclear power plants. So you can use fossil fuels, nuclear reactors to produce the heat to boil the water to turn the turbines. And so the generator then changes mechanical energy into electrical energy. So windmills, they use the wind to turn the generators. You don't have to use steam for that. Other plants use falling water to rotate turbines to generate current. So if you have like a waterfall you built a dam, and you're allowing a waterfall to happen. So you're letting gravity spin past those fan blades, and then it produces the rotation that allows the magnets to spin past the electromagnetic coils. Yeah, this bottom GIF right here, it's totally not working. I'm not sure why, but don't allow that one to confuse you. Okay, last thing for this part. So there's two types of current. There's direct current, and that's current that flows in one direction. So electronics that use batteries use direct current. And so electricity flows in one direction because that's pretty much how batteries work, right? All the electricity is in the battery, and then it flows through the device that you're using until it's all used up. Alternating current, electric current that reverses its direction of flow in a regular pattern. It goes back and forth and back and forth. And this is a generator that creates this alternating current. And electricity in our home is using alternating current. And remember, that's just because that coil, while it's turning, it goes past the North Pole and then a South Pole, and then a North Pole and a South Pole. So it alternates. The North Pole pushes the current to go in one direction. The South Pole pushes it to go in a different direction. That's why it is alternating current. Hey guys, that's all we're going to talk about for now, and I'll see you later.